Ultra-high performance fiber-reinforced concrete is an advanced cementitious material that combines high strength and toughness and high durability. These outstanding characteristics make this material a very attractive choice, and it is frequently used for a variety of structural applications, including bridge, high-rise building, and other special constructions. These structures might be subject to high dynamic loading, such as impact and blast. Engineering application of UHPC include protective structure and critical infrastructure. So, like this phenomena. In the frame of a multi-year research project named Protection of Infrastructure Elements from the Effects of Improvised Explosive Device and Blast Charges, that is supported by Arma Swiss Science and Technology of the Swiss Federal Department for Defense, Civil Protection and Sport. We have carried out an extensive numerical and experimental researches, and this research was subdivided in three parts: the material characterization, developed at the Dynamat laboratory, numerical simulation of UHPC plates under blast loading, and the blast test of these UHPC plates carried out at the Ondrik Detonic laboratory near Spitz in the German-speaking part of Switzerland. The research was aimed to study the retrofitting system using ultra-high fiber reinforced concrete, and different sandwich plates were tested dynamically using C4 charges in contact and standoff distance of 3 and 6 centimeters. The mechanical characterization at a high strain rate was performed in different loading modes, such as the direct tensile test, the compression, indirect tensile test, shear, using sample having different shape, size, notches, and so on. We have analyzed several commercial UHPC having different fiber contents with different aspect ratio of high carbon striped fiber. And I'm going to present you some results on the high strain rate behavior of UHP FRC in compression. To perform this study has been used a new apparatus designed to analyze the triaxial behavior of quasi-brittle material, such as rocks and concrete, under dynamic loading. This machine is currently under construction and was partially funded by the Swiss National Scientific Fund. It consists of 3 pairs of bars in 3 perpendicular directions, and a pulse generator that is a pretension bar in this position. The pretension bar is pulled by means of an hydraulic actuator of 4 meganewton, and the brittle bolt that is placed in between that with this its raptor activate the test. The input bar is the solid continuation of the input, the pretension bar, and the other 5 bars can be considered as the output bars, and each one is at the end of these 5 bars there is other 5 hydraulic actuator that permits to impose the triaxial state. All the bars are instrumented with the string gauge in order to record the wave propagation in the system. The results I'm presenting you were obtained by using only the monoaxial configuration, the actual configuration, this is one, where the specimen is pre-strained before the dynamic test. The imposed pre-strain were 1 and two-thirds of the quasi-static strength. Dynamic tests were carried out at the same velocity by imposing 500 kilonewton in the pretensional bar, giving a stress rate of 1.6 terapascal per second. This is the graph in which you can see the evolution of the cracking process, and this is the response of the UHPC and HPFRC with different preloading in terms of stress versus time curve. All the tests have the same gradient up to the first 60 microsecond. Afterward, the stress versus time curve changes due to the presence of activated crack during the preloading process. Activated cracks and the stress rate play a crucial role in enucleating the cracking process that results in spaceman failure. The material had a more uniform response in tests with higher static preloading values, but its strength was lower caused by the quasi-static loading in case of UHPC, while in the fiber-reinforced material do not present significant differences. In the next two slides, I'm presenting the results of the two materials with the same preloading conditions. This is the results for the matrix, the UHPC, in which this is the evolution of crack, and this is for come on. This is an example of fiber reinforced material. In this slide, I've shown the comparison between the two material, matrix and fiber reinforced one, in terms of experimental stress time curves. The peak load seems not be influenced by the presence of the fiber, while the post-peak is governed by the fiber content, and this influence decrease with increasing the spaceman length. We have observed that by increasing the stress rate, that the shear failure occurs with a higher stress rate. Thanks to the results of more than 400 dynamic tests, an example of on samples with different size, shape, notch geometries under different failure mode, a new model was developed. This material model is named DAMP, Damage Propagation Model, where the damage and interfere with the wave propagation, and we have considered this phenomena. This model was used to simulate the blast loading on the sandwich slab, obtaining very good similarity with experimental results. The entire system was modeled by using LS-DYNA, explicit solver with hexahedral elements, and the experiments were simulated by integrating the constitutive equation of our model with the boundary condition setup of the UHPC and the fiber reinforced material. This slide depicts the damage evolution of the two materials, indicating the color indicated one for a fully damaged and 0 for intact material. And this shows the good suitability of the DAMP model in reproducing our test. Here is the comparison between the stress versus time curve obtained experimentally and numerically for the 3 dimension of samples. The good agreement between the experimental and numerical results is due to the fact that DAMP material model evaluates the interaction between damage propagation, loading wave, and spaceman size. To conclude, to fully understand the dynamic behavior of this material, a comprehensive experimental campaign is necessary to gather information about the material response under various loading conditions and across a wide range of strain rate. For a realistic assessment of a structural response under blast or impact, numerical and analytical methods must be utilized. I'd like to thank our sponsor, Arma Suisse, and all of you for the kind attention.